How the fuck do you draw something on your screen? That shit's fucking insane. It has to be black magic or something. Or does it? Rendering stuff on your screen is not actually that hard, especially if you're not concerned with nerd shit like optimization. To prove how easy rendering something on your screen is, we're gonna make a ray tracer with the only assumption being that we can color a pixel. That's it. We call the computer screen on which we can color any pixel a canvas. This canvas is what's seen by the user. The canvas is an image of a scene taken by a camera. The scene is like a 3D landscape where we can have different objects and, of course, the camera. Um, let's assume you're an untalented painter, but you really, really, really want to paint a picture of your toilet because you're an insane fucking freak. What you can do is you can place a fishnet in front of the toilet and then draw grids on your painting canvas. Then place the major color that comes through the cell on the fishnet to the corresponding cell on the canvas. If you do this for each cell on the grid, you'll end up with a very low res image of a toilet. In the context of computer graphics, the viewport is the fishnet in the above example. We place the viewport in front of the camera, and by adjusting its size and the distance from the camera, we can adjust the FOV. Now, let's assume we have a bunch of spheres on the scene. We use spheres because we are lazy bastards. Spheres are simple to represent because they can be uniquely represented using just a center and a radius. So what we do is we fire a ray from the camera which goes through the viewport. If it hits the sphere, we take the color to be the color of that particular cell in the viewport, which is then mapped to the canvas. The mapping of the viewport to the canvas is just this simple intuitive coordinate transformation. Mathematically, a ray from a camera can be expressed like this. We assume the camera to be at origin and the direction of the ray to be d, which is nothing but the point of the viewport minus the origin. We can check if the ray collides with the sphere using basic linear algebra that goes something like this. Essentially, if we have two solutions to this linear equation, it means the ray passes through the sphere. If we have one solution, that means the ray just grazes past the sphere. And if there is no solution, it means the ray does not touch the sphere. When we solve this equation, we get values of t, which is the parameter. If we get a value of t, we can automatically assume the color of the point of the viewport through which the ray passes to be the color of the sphere that the ray touches. Being the chat that we are, we're going to implement lighting next. We're going to make a few assumptions about the lighting. The first is the assumption that all the light is white. We also assume that the distance does not have an effect on the intensity of the light. We also have three types of light sources: a point source, a directional light source, and an ambient light source. A point source is just the emission of light in all directions from a fixed point on the scene. A directional light source is just the emission of rays in one direction. And an ambient light source is something that gives the same amount of light to every point on the scene, like a minimum amount of light emitted by each object on the scene. We do this because we care about indirect light. When light strikes an object, it gets reflected. So each object reflects some amount of light, which hits the other objects and so on. But it's kind of tricky to keep track of each and every ray as it reflects from object to object. So instead, we just give an overall amount of lighting to each object. Our task is pretty simple. Find the intensity of light that reaches each point of an object and multiply the color of the point by the intensity of light reaching that point. To find the intensity of light reaching a point, we must first figure out the nature of the object under consideration. If the object we're considering is matte, we use diffuse reflection to compute its intensity. And if it's a glossy object, we use specular reflection. Diffuse reflection operates under the assumption that every light ray that hits an object is scattered back into the scene equally in every direction. In diffuse reflection, the intensity of reflection depends on the angle at which the light strikes an object. If the if it hits an object orthogonally, all the light is reflected back. We represent the intensity of light using the width of the ray. So we can just project the ray along the vertical axis using cos alpha to get the intensity of reflection. With the intensity being maximum if the angle between the vertical axis and the incident ray is zero. We can get the cos alpha using simple linear algebra, which looks something like this. So to get the overall intensity of light reaching a point, we sum over all the light sources and add the intensity of the ambient source. Shiny objects look different based on the direction we look at them. The more polished an object, the more it behaves like a mirror. Light is not scattered equally in all directions for a shiny object. For shiny objects, there's a greater concentration of light rays above the direct reflected ray. Not all of the rays are reflected along R because a shiny object is not a perfect mirror. We can model this using the powers of cos alpha. Cos alpha to the power of something like 500 represents an object that is way shinier than, for example, an object that is modeled using cos alpha to the power 200. We call the power the specular exponent. The higher the specular exponent, the shinier the object. We can represent the whole reflection equation like this. Now we have something that looks kind of cool, but we're still missing something: shadows and reflections. The reason that our current rendering model does not have shadows is very simple. It's because light rays can travel through objects in our current model. To solve this, we just need to do something like this. If there's a sphere between the viewport point and the current sphere, then we just skip it, thereby not giving it any intensity. And just like that, we have shadows. Reflections are trickier. If you think about it, reflections on the surface of an object are nothing but images taken by a camera placed on top of the surface. This is how recursive ray tracing works. If we set the number of recursive layers to 2, that means we take an image of the scene and then we take an image of that scene from the perspective of each object. If we set it to 3, that means the reflections have their own reflections, and so on. We implement it through backtracking. Looking at these results, it might be a bit hard to believe that the only capability we have is to place pixels on a screen. But that's all we did. We have our very own ray tracer from first principles. But video games usually don't use ray tracers. They use rust tracers, which are much more cooler and much more alpha. We can make rust tracer too from first principles. But that is something for a future video. Subscribe, fuckers.
See ya.